Okay, so in this video, we're going to look at the proof of the Laplace of u of c of t times f of t minus c is equal to e to the c minus s f of s by using the definition of Laplace transformations, right? I did not go over this kind in my original definition video, and it's possible that your professor might, if he's that kind of guy, might ask to do this using the definition. And you'll have to show how to do it, right? So, to do it, we start with the definition. If you remember, the definition is as follows: 0 to pi of e to the minus, what was it, cs? No, st, right? Times f of t. Now, f of t in this case is all of this. dt. Now, just remember, starts at 0, goes up to f of t minus c. So our bounds are not going to be from 0 to pi. We're going to have two different integrals here that we have to add together because of this. These are two f of t's, think of them. Right? We have when it's greater than or equal to 0, less than c, and we have when it's greater than or equal to c. Okay, so we have two different integrals here, right? For 0 and f of t minus c. So if I rewrite that now, for f of s, we have 0, the integral of 0 from 0 to c, which is obviously just 0, plus integral c to infinity of e to the minus st f of t minus c dt. Okay, so now we have to take the integral of that. So let me just go ahead and rewrite this. Okay, so how would we do this one? Well, first of all, we have our two cases, right? When s is equal to 0 and s does not equal 0. So if we look at our two cases for s equals 0 and s does not equal 0, we'll have the limit to be from c to a of e to the 0 is 1, so f of t minus c dt. If we integrate that, that's just a function times, well, the integral of f of t is just f of t. Yeah. Now let me add a page here. The integral of that is just f of t minus c. So we have where is it? Obviously, we can't really integrate this, right? So, you can kind of think of it like, no, you can't really integrate this. But anyways, if this was any kind of function, say it was just t, whenever you take the integral of this, let's say for example, it could diverge, right? Or it could also be something like this, though. And if it's like this, well, like this, that would converge to 0. This one would diverge. So you really just don't know what's going on with this one. So you could say can diverge. So we're gonna exclude that one. Right? Now if you look at when it does not equal 0, we have to do the whole integration thing. So in this case, we have to do a u sub. We're gonna make u equal to t minus c, and we're gonna have du would be just dt. So then I'm gonna rewrite the bound. I'm gonna rewrite the bounds. I'm gonna rewrite the bounds. So if we want to remember how to rewrite bounds, if I want to rearrange this in terms of du, right? Because if I want to do this in terms of du, I should change the bounds. So if I'm to plug in well, first of all, this would be u plus c. So then when you plug in, this would be u plus c. Which, if I change the bounds, if I plug c in for t, we get u is equal to 0. If I plug in a in for t, I get a minus c. So those are our new bounds now. Zero to a minus c, this would be e to the negative su, e to the minus cs, f of u, du. This would then be, this is a constant, right? It has no u term in it. Pull that out, we have e to the minus cs integral 0 to a minus c, e to the minus su f of u du. Right here, if we get rid of this limit and we kind of go back a step, we can write this like this. Remember, anything like this is always just going to be equal to why can't I draw it? Oh man. Why can't I draw it? Okay. Good enough. Right, so this will be equal to infinity. So then we have zero to infinity of e to the minus su f of u du. Now, you might recognize this is the definition of Laplace transformations, f of s. So if I'm to rewrite this, our f of s is equal to e to the minus cs. I should have included f of s equals all throughout this, but you get the idea. So we have this, right? I didn't have to integrate this, so we didn't have to worry about the whole s greater than 0, s less than 0 thing, whatever. So we just stop there, and we go right to here. So this is this. So here's the proof. Now, what if I wanted to go from this and do the inverse Laplace and go back to... now I want to go back. Now, let's do this. Now we want to go from... I'm going to take the inverse Laplace to get to u of c of t, f of t minus c. This is what we're going to do. So inverse Laplace of e to the ct, f of t, no, we're just going to take the Laplace of this, yeah. 0 to infinity, e to the minus st, e to the ct, f of t, dt, so I have this. We can pull out that e to the ct because it's a constant. 0 to infinity, e to the... actually, no. Let's not do this. Let's just do this. Let's just combine these together. Yeah, let's do that. And then we will do our... oh, actually, this is it. We stop right here. You'll notice that in our typical definition, we have e to the minus st, right? We have our f of s is equal to right, what do you see different here? So that's it. That's it. F of s minus c. Right? And that, of course, would work for whatever bounds you're working with. So if we're going from, 0 to c, c to infinity, then you can just, do your, that's where that comes from. It's pretty cool. All right, so in the next video, we're going to look at some inverse Laplace. Just taking the inverses by using the table, of course, of just these ones. And we're going to use these new inverse Laplace things that we've learned. So I will see you in the next video.